Up until now, we've been talking about Le Chatelier's principle and equilibriums, and we've been talking about acid rain, and now we're bringing them all together. These dot points here are going to be dealt with across the next two video clips, and you'll see them pop up as colour-coded parts. First of all, hydrochloric acid. We normally write HCl, and we're generally referring to aqueous HCl, but it's actually made by putting in a molecule of hydrogen chloride gas into water and allowing it to dissolve. And as it dissolves, it actually breaks it up into ions, pretty much in the same way as this hydrogen bromide does. When it's in water, it gets attracted to the hydrogen here, gets attracted to the water molecule, and it leaves the electrons behind to form the Br minus, and the electrons that over here on this oxygen have attracted the H plus, and it's formed the H3O plus that you can see here. And the evidence for this comes when we start looking at what happens when we try and pass an electric current through it. Now, if the hydrogen chloride gas is dissolved in something that's non-polar, like hexane or benzene, then it doesn't allow a current to transfer through it because there's no ions being formed. It only forms an ion. It only forms ions once you put it in the water, and then it is an electrolyte, and it will allow the current to pass through because of the ions in the water. Without the ions, it doesn't conduct. The other two things that I've been quite worried about with acid rain have been nitric acid and sulfuric acid. And nitric acid has only got one hydrogen attached to an oxygen, which is attached to an electronegative element with a double bonded oxygen there as well. So all of this acts to pull the electrons this way, and this makes this bond very easy to break when it gets near to the water molecule, which steals the H from here and makes this hydronium ion and a nitrate ion. And that happens 100%. As soon as that goes into water, 100% of it will ionize. In the same way, if you've got sulfuric acid, now you notice with sulfuric acid, you've still got this double bond O and the oxygen and the hydrogen there, making this whole area very electronegative. That shared pair of electrons, that tends to stay with the oxygen. If a water molecule comes along, this becomes very easily attracted to the lone pair on the water molecule, and it snaps off very easily. And it'll form the hydrogen sulfate first, 100%. That reaction goes to completion. But the second one that breaks off, that is actually an equilibrium reaction in the formation of the sulfate ion. So it's a two-step process. The first step here is, notice the arrow shows it going to completion, and you notice the arrow here shows it's in equilibrium, even though it's very much favoured towards this side. So we've been more concerned about nitric acid and sulfuric acid in acid rain rather than carbonic acid, because carbonic acid's a weak acid. So when we're talking about strong and weak acids, we're talking about something that's to do with the nature of the atoms in the acid. We're not talking about whether it's concentrated or dilute. Concentrated means that I've got lots, that concentration is related to the number of moles that I have dissolved into my solution. So both these representations here are of concentrated. There's a lot of particles in the water. Both of these are dilute. But when we look at this one, this is a concentrated solution of a strong acid, which has 100% broken apart. And this is a dilute solution of a strong acid, which is 100% broken apart. This is a concentrated weak acid. So there are lots of molecules in this small space, but not very many of them have actually broken up into ions and ionized. And this is a dilute representation of a weak acid. Again, most of it is in the molecular form, not much of it has broken apart. So be careful of these words. Strong and weak is to do whether it is sulfuric acid or carbonic acid, and concentrated and dilute are moles per litre. So in weak acids, we've got this equilibrium situation going on, and we represent that with the anion and the hydrogen, and it forming the hydronium ion and an anion. When we do this, this is acetic acid, which we find in vinegar, and it's another example of a weak acid. That's the H plus that breaks off. A lot of these carboxylic acids here, the electrons are drawn in this way, and that's broken off, but it's not as strong as the sulfur or the nitrogen in this position. Because sulfur and nitrogen in that position are both more electronegative. They've got more of a pull to them. So these are completely strong acids that have dissociated. These are weaker acids where most of it is still in the molecular form and still completely like this. Very little of it has actually lost the H plus. All right, and there are two ways of measuring how that's happened, and one is the pH and the other one is the degree of ionisation. So the degree of ionisation is just a percentage. Out of a certain concentration of moles per litre that we dissolve, how much of it has formed H plus ions, and turn that into a percentage. So if we're looking at a solution where it's 0.10 moles per litre, that's the concentration. If it is a strong acid like HCl, there's no molecules in the solution and it's all ions, 100% of it. But if it's something like HF, which you would think it would be similar, but it's not, because the fluorine undergoes hydrogen bonding and it recreates the acid back again. So you'd get about 25% of the acid actually breaks up, and 75% of the acid remains as the molecule. Whereas with the acetic acid, it's only about 4% that actually breaks apart, and the rest of it remains as the molecules. Now, we keep talking about things like being proton donors, acids being proton donors, and this is a shared pair of electrons. So let's take a look at this hydrogen that we keep referring to as a proton. And remember, hydrogen has got one proton and one electron. This electron here is being shared inside this bond, and this proton here is what is going to leave the atom when it forms this hydronium ion, and the electrons are going to be left behind, and this will become negative, as you can see there, the acetic acid ion. You can get a concentrated solution of that. That's nothing to do with how much of it actually breaks apart. A concentrated is how it's 17 moles per litre has been dissolved, but not very big a percentage of that is actually going to break apart or dissociate and ionize. Okay. Now this that was a monoprotic acid, one proton. This has got two of those carboxylic acid groups. These two groupings here are able to undergo equilibrium reactions and remove those hydrogen ions, and that makes this a diprotic acid. And that's malic acid, and that's tartaric acid. Malic acid's used to give, lollies an extra bit of sour if we want them to have it. Tartaric acid is used as an anti-moulding kind of agent, and it is also diprotic. So these protons here, those are completely non-polar. They're not going to do anything. This one's polar. It will help it to dissolve, but it won't actually break it. It won't actually break here. It'll just associate with the water molecule and allow it to mingle with the water molecules in the same way the tartaric acid will there. This is benzoic acid. This is monoprotic, and it's got that one carboxylic acid group and a benzene group, and these are all non-polar, so it's not terribly soluble. This is vitamin C, which is ascorbic acid, which isn't quite the same thing as citric acid. It's even though you get vitamin C in citric fruits, citrus fruits, there is that acidic aspect to it there, where this OH is going to break off easily, and possibly even that one. So this is a vitamin C molecule. And that's different to citric acid, which is a triprotic acid. It's got 3 of these groups, these carboxylic acid groups, that are easily able to donate a proton. And that's there in citrus fruits. And it's, again, a weak acid, but 27%, 27.5% will actually ionize. Whereas hydrochloric acid is 100% ionized, and acetic acid, which you get in vinegar, is only 4% ionized. And these are some really great videos, and I'll show them to you in the next clip.